There are two cases here. One has a mass on a table. They're two modified Atwood's machines. This is K, by the way, of Unit 2 AP Workbook. This is attached to a 10 kilogram mass. This one is a mass on the table, same mass, same position and everything, same kind of pulley, but now someone's pulling with 98 newtons. So we're going to kind of examine this situation. So first we're going to draw free body diagrams for mass M, big M, mass little m here. So this one has balanced forces pointing up, 1, 2, 3, 4, 5, and down. So the weight here is equal to the normal force because there's no acceleration up and down for this object. There's also a tension force going this way. So we're going to say 1, 2, 3, 4, 5. We'll make that 5 for the sake of argument. And there's going to be some smaller friction force. I know there's friction because they say it's on a rough table. Friction, since this is going to accelerate to the right, it's going to move to the right, net force has to be the right, so friction has to be smaller than tension. Okay, for the hanging mass, the tension has to be the same because it's equal and opposite forces. So 1, 2, 3, 4, 5. Here's the tension again, but now there's got to be, since it's accelerating down, and moving down, then the weight force has to be bigger than the tension. So we'll make this 1, 2, 3, 4, 5, 6, 7. So there's the weight of this object. So let's just check to see if that agrees. When we've got, mass little m is less than mass big M, so I have to fix this. So I'm going to make this a little shorter so that I can keep this bigger than tension, but make it smaller. So this is 5 down, so we'll make this 4 and 4. I'm going to have to adjust a couple of these, and you notice like this is normal, so I'll just make this 5 down, and then I can make this a little bit bigger here, and then therefore this has to be bigger. So there's a whole little chain of events, and don't be scared to correct your preconceived ideas. This going through this process is pretty useful. I mean, I never really worried about that until I started working, doing these workbook problems that they provide, where they ask you to do this to scale. And what it makes you do is think through the relative sizes, like what actually makes sense, right? And so it's a good process to go through. I highly recommend it. Then they tell you that the block accelerates in both cases, but the block reaches the right edge of the table in less time than in case 2, even though the force on the string is the same as the weight of the hanging object in case 1. This occurs because there's a different amount of tension in the two cases. So why would that be? Okay, so in the first case, we had the acceleration, if you look at this free body diagram, is Ft and Fgm. So the net force is going to be MAY, it's going to be FGM minus FT, and I'm making my positive down because the acceleration here is downward. So I'm going to make positive down and positive to the right. So this way is positive, this way is positive. That's why I'm writing it that way. And that makes sense, right? Because this force is bigger than that one. So that's not a bad way to think about it. So you can see your acceleration is due to this difference in the two masses. This is case 1. For case 2, you're only going, so when you look at case 2, you're going to have the Fg, well, not the Fg, this is the pulling force, is 98 newtons. Because this force of the pull, is 98 newtons here, that's going to create a tension force here of 98 newtons. That's how hard you are pulling it. Here, the tension force has to be less than 98 newtons, because in order to get a positive acceleration, you have to have a tension force that's less than 98. So because the tension force in case 2 is greater than in case 1, the acceleration is greater, and therefore it will take less time to reach the end of the table. Okay, this can also be explained by considering systems. Let the system in case 1 consists of both the hanging object. So let's just sketch that, right? It looks kind of like this, right? It's both of these objects. We can make the line of action down. In terms of drawing forces on this, external forces would be this one, Fg capital M, Fg little m. Tension is now internal, and your line of action, as I said, is if we make it down, that means the only force acting, and I forgot friction here. So the only forces acting along the line of action are friction and this weight. So I would write we'll call that the x-axis, even though it's a line of action. You would have Fg little m minus the friction force equals mass times acceleration. And this is the sum of the masses, m plus m. And on the case 2, right, you've got a direct pulling here, right? There's nothing else acting on, there's no block here, right? You're just pulling straight down on the object. So you've got this 98 Newton tension force, and you've got friction. And that's acting on this line of action. There's no, this equation doesn't really change. You've got Ft minus FFK equals MAX. And this here is 98 directly where this is also 98 and friction is assuming to be the same, right? So whatever this is, FFK, but look at this. This has 2 masses it's dragging along. So I'm dividing. So I get 98 minus FFK over m plus m equals your acceleration. This one is 98 minus FFK minus just the big M, right? Just the mass of the big object. So you're dividing by a smaller value, so your acceleration is going to be bigger. This is called system solving, and it's really a great way to analyze. I prefer this way to this way. This takes a lot more work mentally than looking at the whole thing as one system.